to practice that on the heat equation. And we talked about using the energy method to prove uniqueness in one dimensions and two dimensions. And that follows a similar kind of approach to how you used an energy method in the case of the wave equation. So the maximum principle is an alternative way to prove uniqueness, but also it's useful for learning about other properties of solutions. So what's the main idea? Essentially, the main idea is that smooth solutions obtain a max and min, because you can take the negative and say that the negative of the solution obtains a max, either initially or on the boundary. Okay, and we sort of hand wave through why we should expect this to be the case with the heat equation. It's because of the smoothing properties of the operator, and about how we wouldn't expect this to be the case in the wave equation, because you can have interference between propagating waves that would lead to an interior maximum. So in order to prove this, we want to just set up some notation. So I'll just redraw the figure that I drew yesterday, and we'll start off with just proving it on a bounded domain, where the initial domain U is equal to just 0 to L, okay, and this is values of X, which could be, well, in this case, we'll just stick to 1D, but you know, you could use an initial domain that's planar or three-dimensional, any kind of Rn, and the time axis is going to go in this direction, and along the time axis, okay, right on the boundary will be one part of what we call the boundary gamma t. The initial boundary will be part of gamma t, and this rightward boundary will also be gamma t. And we'll call this point here that occurs, this line that occurs at t equals capital T and goes from 0 to L, we'll call that part of U sub t, and then the interior here will also be called a region U sub t. Okay, and we're going to need this notation for our proof. So, so just to sum up, this is just rehashing what I said at the end of class last time. T greater than 0 is some fixed time, okay? And we're going to increase that towards the end of the proof. U is some region in Rn. For the purposes of this picture, I'm drawing it as, you know, one-dimensional from 0 to L. This is our spatial domain, or set, okay? U sub t is going to equal U crossed with 0 up to t. This is going to be what we call our parabolic cylinder. And the boundary gamma sub t is going to equal the closure with ut itself removed, which is going to be the boundary from 0 to t, along with the boundary just at t equals 0. Or sorry, the initial spatial domain just at t equals 0. Okay. And this here is meant to be a union. It's not meant to be another U. Okay. So this is our parabolic boundary. Okay. And So what does the maximum principle say? Well, it says in particular, if U lives in this set, okay, which is going to be once continuous functions, once continuously differentiable in time, and twice continuously differentiable in space, okay? And this here can be a mixed partial, right? So if we're in R2, this could be, you know, dx, dy, d2x squared, and so on, right? All of these derivatives should be continuous, okay? If U lives in that set, okay, so that first of all, it's in that set as well as being fully continuous on the closure of that set. And let's say it satisfies our heat equation, right? U, T, I'm running out of space here. I'm going to drop down a line. UTXT is equal to K Laplacian of UXT. Okay. Then in the domain UT, then the maximum over the closure of U of XT is equal to the maximum over the boundary of U, okay? So this is what we're saying. And so again, just to give you a picture of this, right? Imagine you have a very peaked function at this initial condition, right? What's going to happen as soon as you step away from the initial condition, it's going to get smoothed out, okay? You may also have some, you know, source conditions here at the boundaries. You may have some heat flux, right? But so the most heat that you're going to get, or the, you know, largest value of U that you're going to get in that case, is going to be at the boundary if you have a heat source here, and it's going to drop down in between, okay? So depending on whether your heat source is your initial condition or the boundaries, the largest the heat can be is all along the boundary, okay? Either along the boundary or along the initial condition, okay? So this is the theorem we want to prove. We'll prove it momentarily. Before we do, let me make some remarks, okay? First of all, if we suppose that U has some local max at x, t in U sub t, okay? Then, okay, I'm running out of space for this. I'm going to write this again on the next page, okay? Well, let me just sort of, you know, hold on. Let me start these remarks again on the next page. Okay. So what's the idea with the proof of this? So if we suppose U has a local max at xt in U sub t, okay? Then what do we know about local maxes just from calculus, right? Well, we know that their first derivative should be 0, and also that their second derivatives should be negative, right? Because you need the function to be concave upright there, okay? And because we know that the function is C2 in U sub t, then we should be able to compute that, the Laplacian essentially, which is going to give us the curvature of the function there, okay? So let me write these things out. So if we knew that we had a local max, then we would know that u sub t at xt, why did I just write that, is equal to 0. We also know that u sub xi, depending on how many dimensions x is going to equal 0 as well, okay? Because we have a local maximum, right? And we also know that the Laplacian of u is less than or equal to 0, okay? That's just the definition of a local max in multiple dimensions, okay? Now, if the Laplacian of u of x is strictly less than 0, okay, then we know that 0 is equal to u sub t, but we know that that needs to equal k Laplacian of u, which if k is greater than 0, which it should be, then the Laplacian of u is less than 0. So we have a contradiction that 0 is less than 0, okay? So the easy case of this proof essentially is when we have, some strict local maximum, right? So the idea here is that somewhere in the domain, let's say for contradiction purposes, there's some local max here, right? And the function falls off around it so that it's all of its first derivatives are positive and are and the second the derivative, the Laplacian here is negative, okay? That immediately generates a contradiction because it's in violation of the PDE, okay? So we can't have that happen, okay? The more difficult, yeah, go ahead.
So when you say that the Laplacian of u has to be less than or equal to 0 for it to be a maximum, wouldn't that just make it a maximum in space? Wouldn't we also need like the Laplacian of u plus utt to be?
Right. Yeah. I'm just listing the necessary conditions, but I'm not listing the sufficient conditions. So yeah.
But if like utt were large and negative, then the Laplacian could be positive and that would be satisfied.
Um, I don't think that's true. I think it
No?
has to
Okay.
be, yeah, I think it has to be that your Laplacian needs to be negative, right? Because it's going to be
Oh, right.
it's
It's
going to be
all
the
second
it's
derivatives,
going to be
not.
the sum of second derivatives that are all non-positive. Yeah.
Yeah, my mistake. Thanks.
Yeah. Okay. All right. So it's quick to show a contradiction in that case, okay? But the harder case to deal with, right, is the case where the Laplacian of u is just strictly equal to 0. Maybe all your second derivatives are just 0 in that case, okay? So the proof will primarily deal with that, okay? The second thing is that since u is this has the C2 property in the closure of u sub t, okay? And the argmax of u needs to be in the closure of ut. This implies that there exists some x0, t0 in the closure of ut such that u of x0, t0 is equal to the max over the closure of u of u of x2. This is just a statement of there being some particular value xt, x0, t0 at which this maximum is going to occur. Okay. So with those two things in mind, right? Basically the description of a local maximum, and also the assignment